Find the absolute maximum and minimum values of f on the set D. So f of xy is equal to e to the negative x squared minus y squared times x squared plus 2y squared, and D is the disk, x squared plus y squared is less than or equal to 4. My first thoughts here are just taking partial derivatives and setting them equal to 0. This will hopefully allow us to figure out a whole bunch of critical points of f, possible candidates for the absolute minimum and maximum. We will have to keep in mind that we're on this disk, which is a compact set, so the absolute minimum or maximum could occur on the boundary of the disk. So another thing that I might do, the form of f will actually make this quite convenient. I might just parameterize the boundary of the disk. It's a circle, so that'll be easy, and find the absolute minimum and maximum on the boundary, and then worry separately about the interior points. I might do the interior points first with the derivatives, partial derivatives both being equal to 0. Another thing we'll have to keep in mind is partial derivatives being equal to 0 you really do have to worry about second derivative tests, really checking whether you get minima or maxima. I can never remember off the top of my head exactly what you have to do. I think you need the matrix of second derivatives, and you need to compute its determinant. And if that determinant is positive, then what does that say? Then that means you have potentially a minimum or maximum. And if the determinant is negative, that gives a saddle point, I think, if I remember correctly. Anyway, we may not need all that depending on what happens with figuring out the derivatives and figuring out what happens on the boundary. But I'm just going to get into the computations. Okay, so when I go through taking derivatives and setting them equal to 0, I get two equations, x squared plus 2y squared equals 1, and x squared plus 2y squared equals 2. And this, there's no solutions here, right? We can't have x squared plus 2y squared being equal to two different numbers. Let me just make sure I did the computations correctly here before going on. I do in fact have a little bit of an error here. If I look at these two equations, those are satisfied when x and y are both equal to 0. So I can have the partial derivatives. I can have the partial derivatives being equal to 0 when both x and y are equal to 0. So let me get rid of this and cross that out. And what is this? Is this going to be a minimum or maximum of the function? If I think of the function as being a surface, it's got to be a minimum, right? When x and y are both equal to 0, everything here is positive. That's positive. That's positive. So when x and y are 0, the function's equal to 0. And so what I'm starting to think now also is that if I think the function is not exactly radially symmetric, because the level sets of this are a circle, level sets of that are an ellipse. But at the origin, the function is 0. If I spread out from the origin the function should get larger. But then as I get farther and farther away from the origin, this will dominate and everything will decay to 0 again. So it kind of has to reach, I feel like it'll still reach a maximum value. Why do these derivatives not indicate where that maximum value is? I see. There are more solutions here. Goodness. Okay, let me write out properly what the first and second derivatives being equal to 0, what those equations actually say. Certainly, we can cancel out the exponentials, but let's look at what we have here. Okay, so I have shown that when x and y are both equal to 0, that is the solution to this. But watch what happens if I let x equal to 0, what happens to these two equations. The first one is automatically satisfied, and the second one turns into, okay, so I have a whole bunch more solutions. I've got, I have 0, 0, which I've already identified. I have 0, 1, and I have 0, negative 1. These are all possible solutions I'll have to test. We'll notice that these are all interior points. And I suspect 0, 0, we've already identified logically that this has to be a minimum. I suspect that 0, 1 and 0, negative 1 are maxima, because this function's kind of going to go out in, there's going to be kind of like little two bumps in this function. Okay, but also in these two equations, I can also let y be equal to 0. Oops. If y is equal to 0, the second equation will automatically be satisfied, and the first equation turns into, so again, I have x will be equal to 1, 0, or negative 1. Okay, so let's write out all candidate points that we have now. There we go. And I need to evaluate the function at all 5 of these points. Okay, so we've already identified the minimum being 0. These 2 points both give the same apparently maximum. I mean, technically we would have to do some second derivative tests and so on, but certainly if we fix x to be 0 and think of it only as a function of y, this is certainly going to be a maximum just by picturing what the curve looks like. Do we have to worry about the boundary now? The boundary of the disk? These points are all within the disk, so we don't have to worry about missing those points. But I don't think we can possibly get a larger value of the function on this disk, right? As we keep getting farther and farther away from the origin, the exponential part is going to dominate, right? Even if we just ballpark this, f(0,4), this is e to the negative 16 times 2 times 16, and this is tiny, right? This is extremely small. And everywhere on the disk, if I have x squared plus y squared is equal to 4, then f of xy is equal to e. Oh, goodness. Hold on. My, oh my. 4 is not, this number is not on the disk. It's 2, right? But still, x squared plus y squared equals 4. This is e to the negative 4 times 8, which is pretty small. This coefficient is a pretty small number. And if x squared plus y squared is equal to 4, then f of xy will always be equal to e to the negative 4 times something. And that something, in fact, 8 is the largest value that thing can be equal to. So I don't think we even have to worry about the boundary of the disk just by thinking about this reasonably in terms of typical magnitudes of these numbers. I'm going to say that this is this is as far as I'll go. I don't think we need to actually do any more work to figure out the minimum or maximum of this function. But if I find a mistake or have more to say about this, I'll put it down in the description. Thanks for watching.